Yeah, great. I'm Ben Biffard from the Digital Operations Group. I'm the new director, so I'm really busy getting up to speed on all this stuff. And my previous director threw me at this conference, said, "Do this talk." And I'm like, "Okay." So I threw something together here. Hopefully it goes well. Um, I'm going to talk about our data management and archival system, Oceans 3.0 today. As not a upper management, I have to talk about strategic vision. So Oceanworks Canada provides ocean intelligence to enable solutions for science, society, and industry. But basically, we build and deploy the infrastructure to collect the data to gather ocean intelligence, and that can come from internal scientists and people on staff, but also a lot of collaborations with communities, university researchers, government researchers, and all that. And that enables action and change. We're funded by the Canada Foundation of Innovation, which is a department within the federal government, also funded directly by the Canadian government. Province of BC kicks in some dollars, and the University of Victoria supports us mostly with in-kind infrastructure. I'd like to thank this. We're thankful for the support of the many Indigenous peoples who historical relationships with the land and sea continue to this day. And I'd like to acknowledge the contribution of our staff, up to about 150 now, data scientists, software engineers, mechanical engineers, electrical engineers, and a lot of outreach and education staff as well. We collect this data from all these different places all over Canada's 3 coasts and on land, and now from the Southern Ocean. We collect the data for all sorts of very diverse purposes, from supporting the blue economy, like testing instruments, to marine mammal observing and avoidance, earthquake early warning, geophysical stuff. We even have done some forensic experiments. And the primary one is ocean observing, of course. Here's a bit more detail on some of our data sources. We have community observatories. These are small platforms that are usually on short cables in shallow coastal waters, up to 100 and 200 meters deep. We support a community observing program where the communities go out in small vessels and do CTD casts. A CTD is conductivity, temperature, depth, basically an underwater weather station. And that's collected with an Android app. But our main effort is on our deep sea cabled arrays. I don't know if you can see my mouse, but I'm kind of pointing to it here. The red loop there off the coast of Vancouver Island, the Neptune array, and the inshore Venus array, which is where ONC started with. We support deep sea ocean science there, and later this summer, we're going to start deploy the P1 neutrino array, which will be similar to the IceCube neutrino observatory, but in the deep ocean. We also, on land, we also have earthquake early warning sensors. I forget how many, 20 some odd locations all over Vancouver Island. And this basically started with the realization that 2 of our deep ocean nodes are directly on top of where the big one will start. So if you can detect that big one right there and send a warning to the population centers, you can give them between 10 and 90 seconds of warning to prepare for shaking. So that's pretty motivating to make sure our data infrastructure is up and running all the time. So how do we do all this with all the different sources of data and different use cases and everything? Well, we have our Oceans 3.0 complete top to bottom software solution. As you can see here on the right, we collect data from all sorts of different things, from the deep ocean to coastal radar to weather stations on land to gliders, autonomous instruments, offline, live data, low latency and high latency stuff. It began 20 years ago, powering the world's first large-scale internet-connected ocean observatory. It was originally called DMAS, which was an apt acronym, but we tend to veer away from acronyms because it gets kind of crazy with all the acronyms we could have. So yeah, data management and archival system, but now it does a lot more than that, including like cloud computing and stuff like that. So it enables continuous real-time ocean observation, data collection, and communications. Data collected from the cable, autonomous, and mobile instruments in the deep sea, coastal, and land-based locations. Just throw some numbers at you, since we seem to be doing that a lot in our talks, and we do this every time actually. We have over 12,000 active sensors, nearly 1,000 individual instruments. An instrument can have multiple sensors. 284 unique file-based data products. Those are the ones that are currently archived. And the little asterisk there, I'll explain later, that we have about 100 more that are generated on the fly. We run pre-generated data products daily. We actually have a lot of daily data requests, mostly through the API nowadays. We archive about 300 gigabytes of data a day and store about 1.7 terabytes of data in the archive. Doesn't include backups and multiple copies and all that stuff. That's just the uncompressed data volume. So we published an article in a journal a couple of years ago talking about the little bit of history of our data infrastructure. And it goes back to this initial prototype back in 2004, 2006. And this was the first stack, basically the first data center. It goes from the data center at the top, which is a database, web server, visualization software, a shore station, which is a bit of computing infrastructure right where the data comes ashore or comes to land or wherever you can have a computing facility. There's a network switches and infrastructure that build the actual data infrastructure to send the data back and forth. And then when you get down to the instruments, back then, particularly in 2004, almost all oceanographic instruments were done over serial communications, so RS-242. So we had to have serial IP servers to talk directly to the instruments. And then we have, in this thing, there's a relay server that controls power to the instruments. So nowadays, we call that a junction box. This is a bit of the hierarchy of the data center to sensor system. I'll start with the primary data center. We have one primary data center and a secondary backup. They have a one-to-many relationship with the shore stations at all the various spots where the data comes ashore. Then in the deep ocean or shallow ocean, wherever, we have a junction box or a node that connects to the instruments. That's that relay server I mentioned before. And the instruments can often have many sensors. So there's the one-to-many left to right, and then the data flows from right to left. And yeah, commands are sent left to right, and data comes right to left. Yeah. Our data acquisition process is a little bit complicated. I'll quickly talk through this slide here. So we have driver software that interfaces with the instruments. Each bit of driver software is somewhat unique because oceanographic companies who develop instruments tend not to have a common standard. So it's one of our difficulties. The drivers command and control the instruments. They publish the data on this JMS parser queue. The data goes to shore stations where there's a bunch of steps that go on: parsing, calibration, QA, QC, which is quality assurance and control. And we can detect events at that stage at the remote site so they can react quickly. And then we'll archive the data, put the data into databases and file servers. So we use Postgres, Cassandra, and our own file system. And then at the far end here at the bottom, we have a task machine pool that can do all sorts of different value add tasks on the data. The data is available in our Oceans 3.0 data portal, 100% live. The latency ranges from milliseconds for like the earthquake alert warning system, has to be fast, to minutes for instruments that generate their own files. So that's the best example are hydrophones. These are underwater microphones that record 5-minute chunks of audio, and then they send that data up through the network, and that takes 5 to 10, 15 minutes to do that. The backbone of our system is this enterprise service bus. It's Java messaging system, JMS, and our specific technology is ActiveMQ that we use. We used to use an IBM MQ system, but ActiveMQ is better. So yeah, again, at the start, it's kind of a repeat of the previous slide, but on the left here, we have the driver service running on the shore. There's a driver instance at the shore station that interfaces directly with the instruments, produces these data messages, and then it goes along on this bus, and that has multiple steps as it goes along. So parsing and calibration, quality control, quality assurance, event detection, Then it goes into data archive to be archived in the file system and the database, and then we can do cloud processing. The same service bus serves user requests to requests for like processing and various options on the data sets, and that's served through the task machines back to the users. The other cool thing is that our internal staff can command and control the instruments, turn them on and off, configure them, change their data cycle, stuff like that. And that's all live and in real time. Our data center looks like this. This is the primary one. There's a few other ones. Actually, not very far from where I am right now. We use Postgres, as I mentioned, for our main metadata database. It can also be used for the scalar database. And now scalar is a term I should define. Scalar is one measurement per reading, which is like temperature, salinity, wind speed, things like that. Whereas complex data, we distinguish them as things that are normally multidimensional arrays, like radar scan or audio data or video data. And yeah, the data center stores all this stuff, but can also produce data on the fly from the raw data formats. We also pre-generate and archive that data as well. We use another technology called ERDAP from NOAA. It sits on top of a NetCDF data store. We produce those files as well. You probably saw OOI's talk yesterday. They use a lot of ERDAP, and so do we. It's great for ocean data. We've also written a custom Cassandra driver to push the scalar data to ERDAP. And with the well-described metadata, you can then push those data catalogs to a catalog server. We use CCAN to do that, and that then gets listed up on the Canadian Integrated Ocean Observing Systems data catalog that combines data from all the different observatories across Canada. So not just ONC, but the Hackeye Institute, Ocean Tracking Network, and a bunch of others that contribute ocean data. And then that data can then feed up into the global ocean observing system, GOOSE. And I'm not sure if they're fully ingesting it yet, but that's the plan at some point. The file formats we support, the first line here is anything goes. As long as it has appropriate metadata and documentation, we'll support it and store it and collect it. We support the manufacturer's original formats. They're often binary and difficult to understand. We do have a list of preferred formats, including FLAC for audio files, MP4 for video files. But generally, all the data that's collected through our driver software is stored in this raw log hex format. And that format is basically a timestamp and whatever the data chunk is. And that has allowed us to take on 400 different types of instruments, well, maybe 300 different types of instrumentation from, land, sea, air, and all sorts of crazy things. So it's been very flexible for us, and that was the original idea back in 2006. So that's been a very good idea. Our minimum requirements for data for each instrument type is a raw format, the manufacturer's original format if it exists, an accessible data format like a NetCDF or a CSV format, something that users can actually easily read, and then a visualization to plot, and that allows us to do quality control and monitoring. We support over 300 different types of instruments. We support over 400 types of different data products. These are usually generated with Java, MATLAB, or Python. We prefer on-the-fly generation because it's easier to maintain and allows us to offer users on-the-fly options. So like colors and plots. Do you want the gaps filled in your CSV file? Things like that. There's like 100 different option sets. We support citations and persistent identifiers to facilitate reproducibility. And we encourage our PIs, our principal investigators and collaborators, to contribute code to help understand those manufacturer formats and produce value-added data products. We're hoping to do published code and citable code and a complete provenance we're working on. We have most provenance, but yeah. If I have time, I'm going to talk about a few challenges.
Yeah, yeah, you
Um,
still have time. Go ahead.
yeah, I'll go through this fairly quickly. Yeah, I think I have 5 minutes. Bit more. Okay, yeah. Um, I mentioned generating data products on the fly or value add processing or even just base processing of the data that comes back from the instruments. Has a lot of historical code in MATLAB. And if anybody's worked with MATLAB, you know that when you start up MATLAB process, it's really slow to start up. But actually, the processing in MATLAB, once it's going, we don't find it's if the code is well written, which is a little bit harder to do in MATLAB than maybe other languages. If it's well written, it runs just as fast in C or Java or Python. So we still use MATLAB, but we've developed this tool called MATLAB as a service where we create a pool of MATLAB instances that are maintained and choreographed to quickly respond to user requests and tasks. And it basically skips all that startup latency. And MATLAB itself has this optimization caching stuff inside that every time you run it, particularly if you do repetitive tasks, it gets faster. So we've developed this in-house system, and it's been great for our data product generation and processing stuff. Uh, we do have a plan to extend it to do Docker images, so that'll support other languages like R and Python and anything else that people want to run code on. Another challenge we have is when you deploy hydrophones near US Navy bases and Canadian Navy bases, the military want to screen that data um, and divert it when there's ships and stuff going by. So we have to deal with that hiccup in our processing and data acquisition flow. And you see it gets a little bit complicated, but basically the military screening can go in between as an extra step in our data acquisition process. But once the data comes in, we still do the post-processing, the spectrogram generation, parsing, viewing, and all that stuff. But then we have to handle this secure data. The military screening step is done in a secure, locked off server room and a VLAN that's highly secure as well. So the one thing we're noticing with this is that back in the early 2000s, when hydrophones and cable observatories were non-existent, this was really important to do. But now basically anybody can drop a hydrophone in the ocean and connect and live stream it to the internet. So we're working on making this a bit more reasonable for the 2020s. Another great tool we have is CTube. We allow exhibitions that are far offshore on ships to stream data back to scientists on land around the world. And when we do that, they can annotate things like things they see in the video, and they do that on land and on ship, synchronized live in real time. Yeah, so the synchronization between all the databases, between the various ships and onshore systems, offshore systems, data centers was a technical challenge, but we've got some good solutions that are working pretty well there. Lessons learned. Monitoring is a huge benefit to reliability and maintainability of the systems. We have 24/7 on-call staff who's that's their responsibility. We use Grafana to do that and some other tools, but Grafana is great. I've seen Grafana a bunch in the last talk, and I just wanted to mention that. Another thing that we've learned over our 20 plus years, well, almost 20 years of doing this work is lifecycle management for our digital infrastructure, but also the instrumentation. So this slide talks to the instrumentation. We spend a lot of time in step 2 here in development, writing those software drivers to interface with all those unique instruments. And then the testing, we have a facility with a big tank with seawater in it to test all the instruments as they would be deployed in the deep ocean. Then we'll take those instruments, deploy them in the deep ocean or various other sites. There's a commissioning process where our data scientists look to make sure the data is of good quality. They can annotate that data. They can do various other steps to make sure it's of good quality. We monitor those quality assurance and control flags and other tests to make sure the device is functioning well during its lifetime. And if it's starting to fail or running out of its life cycle. We'll recover it, decommission it, or service it, and then we'll loop back around the cycle. This is a whole team process. You can see at the bottom here all the different teams that we have involved in maintaining and lifecycle instrumentation. We have built a number of tools inside Oceans 3.0 to facilitate this. So this is our workflow tool. It links to JIRA tickets that organize the teams. And we also have user interfaces for all the quality assurance and control tests and systems as well. This one configures these various range tests on this Antarctic observatory. Does it say Antarctica? I can't remember. Yeah, this is the new Antarctic observatory. So we're the range tests and stuff are interesting for that one. Great. And just my last slide here. Our foundational infrastructure was designed to be scalable and to facilitate all phases of data acquisition. So I know this conference is about from instrument to first storage, but we've learned that considering the entire lifecycle and distribution of data is really important. So we support video players, scrolling image players, preview, search, plot, and download. But the thing that's really been catching on lately is API and a bit of cloud computing as well. We support all of that. So putting it together has been a game changer for scientists and society. We can do things like earthquake early warning, tsunami warning, observations of climate change, biodiversity. It's been incredible. And for more information, I've got a link to our comprehensive paper. You can go to our website and you can email me if you like. Thank you very much.
Thank you very much, Ben. Any questions from the room?